there's not really a gentle way to do this, so let's just go ahead and rip off the band-aid, so to speak. Uh, we talked about these things. We've been talking about Riemann sums, these approximations of areas, which we've seen area and definite integral are kind of one and the same thing. So the idea we laid out at the end of the last video was to get a true value for this thing. It felt like we were going to end up having to do some kind of limiting process as we let the number of these rectangles we were using in our summations run off to infinity. As it turns out, that is kind of the case. You can actually generalize this a bit more, but we don't really need to for the purposes of this course. There's a handout posted in Moodle that kind of lays out, so long as we make sure we're picking some x of k value inside each of these little intervals that we're dividing the big AB interval up into, it doesn't really matter how we pick them. So left-hand sums, right-hand sums, midpoint sums, they all end up approaching the same thing once we apply a limit. So just as a reminder, we're going to end up using these guys a fair bit going forward. Delta x, that's the width of each of these intervals. It looks like that. In the examples you're going to see here, we're not going to have a number we're plugging in for n, because it's kind of the variable we're leaving around and we're taking a limit with respect to. As I said, it doesn't particularly matter how we pick the x of k, for this. So for convenience, this is the most elegant formula I think we can end up using for this. Officially speaking, this would be measuring right-hand endpoints. So if you wanted to track that, this is technically like corresponding to what we do with that right-hand Riemann sum. So keep that in mind. Our textbook's notation is a little bit different than what I tend to use. They start all of these divisions and they call the first point x1. I've always started with x0, so if you look in the text, the formula is a little bit different. It's going to shake out to be the same thing here, so don't stress over much. Okay, so let's take a look at this in the context of our two examples that we've already looked at in terms of estimating integrals using Riemann sums. So we were looking at the definite integral from 0 to 5, and the function we were interested in was 2x cubed plus 1. All right, so I'm going to work out my delta x, which isn't too tough here because one of the endpoints is 0, so he just kind of goes away. So 5 over n. My x of k, I'm going to feed in my a value of 0. K is the index of my sum. I need to keep him around. Delta x, we just worked out. So it looks like 0 plus k times 5 over n, or 5k over n. Okay, so we've got delta x, we have x of k. Now we've got to fill in the blanks of this formula right here. So bear with me, I need board space for this. My apologies for the jump cut. I'm really not a fan. You can ask my wife. Anyway, so setting this thing up, our definite integral is going to be the limit of these right-hand Riemann sums. So now I need to take that formula I worked out for x of k and plug it in here into my integrand, the function inside the integral. So I'm going to have 2 times 5k over n to the third plus 1 times my delta x, which I'm going to feed in, that was 5 over n. Okay, so buckle up. We got a lot of algebra between us and the end of the tunnel here. So, all right. So we've got our sum. 5k over n quantity cubed is going to be 125k cubed over n cubed. Then I have to double that. So that's going to be 250, 2 times 125, k cubed over n cubed plus 1 times this 5 over n. So if you need to write out what happens when you multiply that thing out 3 times, it's okay. No judgment. Now I need to distribute the 5 over n. Technically you don't have to, but I think it makes this cleaner to follow. So So we'll have 250, oh, sorry, 1,250, because I have to multiply the 250 by 5. K cubed up top, n cubed times n, gives me n to the 4th down below, and then I just get a copy of 5 over n when I multiply that part together. So, all right. Now, I don't want to skip too many steps at this stage. So what I'm going to do here is actually break apart the sums. So I can pull out this 1250 over n to the 4th, because it's a constant as far as the index of the sum is concerned. So long as it doesn't have a k on it, I can pull it out front. So I have 1250 over n to the 4th times the sum of k cubed as we let k go from 1 to n. And then same old linearity stuff we've been doing all semester. We have a sum of a whole bunch of 5 over n's in the back. Okay, so now we can call in our summation formulas that we saw when we were talking about sigma notation to deal with each of these guys, and then we can stop writing awkward Greek letters and just focus on the amount of algebra we still have in front of us. So bear with me for just a second. I could probably let you watch me erase the board, but it's not exactly exciting watching, right? So, all right, at this point, we had the 1250 over n to the 4th. We were summing up k cubed, right? So our summation formula for k cubed looks like this. So we have n squared times n plus 1 quantity squared over 4. On the other side, we were summing up a bunch of constant 5 over n's. No k was there at all. So our formula there was we just take whatever the constant is and multiply it by n. Okay? So I normally recommend at this point students clean up what they can when we have neatly factored terms. It's kind of handy. Like, for instance, we got an n in the bottom and n in the top. They go poof. You can cut this down because each of these guys is an even number, so you can divide them both by 2 and get 625 up top, but 2 down below. More importantly, we've got 2 copies of n right here and 4 copies of n in the denominator, so I can get rid of the n squared up top and knock the bottom down to an n squared itself. Okay. Now, I'm going to expand some of this stuff. So again, 1250 divided by 2, when I cancel down here, gives me 625. I'm going to FOIL out the n plus 1 quantity squared. Let's see, 4 divided by 2 gives me a 2, and I get 2n squared there. And then in the back, I've got plus 5. All right. Now, I want to take the limit of this thing as I let n run off to infinity. So, well, 5 don't care. There's no n. 5 just wants to be 5, Dad. So we've got that right there. This guy, he's a rational function, and if you think way back to when we were talking about limits in chapter 1, we saw how to deal with limits of rational functions like this as we let n get bigger and bigger and bigger and bigger. You get the idea. We look at the highest power terms. We have a second degree n right here, a second degree n right here. Those match, they're equal. When that happens, as we saw back in chapter 1, the limit is going to be the ratio of the coefficients of those high power terms. So the coefficient down here is 2. The coefficient of n squared here, if I distribute the 625, which if you want to do that, have at it, would be 625. So we have 625 over 2 coming out of this guy. 5, again, just wants to be 5. So there's no n anymore. We've taken care of the limit, and we can combine our terms. 5 is 10 halves, so that would be, what, 635 over 2. So now, instead of having an estimate, that is our precise area through the magic of calculus. So if you take a look, this does happen to fall in between our 2 estimates from the left and right sums from earlier, so we really did have like a bound on each side of those guys. So 1 down. Needless to say, it's going to take me a bit to set up the next example, so let's go ahead and punt on that until we record another video.